back. In this video, we're going to talk about motors. Okay, the first type of motor that we're going to use in embedded systems are called stepper motors. Again, I'm not going to drive too far in the weeds, so I'm going to present some of these characteristics, but we're not going to go too in deep because I want to keep this nice, short, and pithy so that you get the concept, and then when we play with them, you'll see how they work. Okay? So, stepper motors convert electrical energy into rotational mechanical force. Okay? We've got power to a motor and we want to turn a shaft so that something either rotates, moves, steps, whatever it is. Okay? We want to make a rotation. Now, stepper motors are called stepper motors because they rotate in steps. Okay? So it's going to rotate at precise rotational angles. Okay? That's how it works. Now, it has a stator which is fixed and it has a rotor which spins. Okay? And spins can be a step at a time based on how the power comes in to the motor. Now, there's a term called variable reluctance because there's an iron core with minimal reluctance to create minimal reluctance between the stator and the rotor. In other words, you want it to be willing to move. Okay? And so that variable reluctance helps create the ability for the thing to move freely. All right, there's a permanent magnet. The permanent magnet is the motor is either repelled or attracted by stator to the stator by the different pulses. So you change the pulses and all of a sudden it's going to want to go like this. Then it's going to want to go like this. Then it's going to want to go like this, or it's going to go backwards. So how you apply the power to the prongs of the stator relative to the rotator, okay, basically that's going to determine the rotor is going to spin in either direction or as many steps as it needs based on the power and how that's sequenced. Okay, so again, I'm not going to go into that right now. We may do that later in another video, but that kind of drives away the point that you're going to change the power signal to the motor and it's going to move rotationally in steps, and that's the point I want you to know right now. Okay, and there's a hybrid synchronous type that is a combo of variable reluctance and a permanent magnet. So the permanent magnet uses the repelled thing and the variable reluctance uses an iron core, and then you can use both. Okay, and it's kind of a hybrid, and that's really the best one that's used as a stepper motor. They're typically mostly hybrid these days. Okay, so stepper motors. A full step is 360 degrees a turn. It's just going to rotate once. Okay, it's got half mode, but don't be deceived. Half mode is going to take 8 steps typically to get all the way around to 360 degrees. Okay, and then it has micro steps if it's a good stepper motor, and that can be anywhere up to 256 degrees, or excuse me, 256 steps to get the 360 degrees based on how it's manufactured. Okay, so some of them will be different in how many degrees they will move in microstep mode, but a microstep motor will get you very tiny steps to do 360 degrees. You're moving a couple degrees at a time. Okay. Typically for a stepper motor, you're going to need an external motor driver, basically either a power or a sync source with enough power to operate the motor. Okay. Typically the signaling electricity is not enough to also run the motor. All right, so it's going to need a power source and the signaling will be separate. Okay, and you are going to see that. Okay, advantages of a stepper motor. It's accurate position. You know exactly where you've rotated to. You can calculate based on a given stepper motor's angles and the mode you're in. You can say, okay, it's going to rotate this far every time I do it. So I need to rotate 180 degrees, 270 degrees. I'm going to give it that many steps so that I get what I want. Okay, it's very accurate. And they hold torque very well. Okay, it can hold its position and the torque on the motor really well. All right, disadvantage, it doesn't move very fast. You can't get high speed out of a stepper motor. Okay, it's measured angular movement, So you're just not going to get high speed out of these things, okay? And it does consume power to hold the torque. So it's good at holding the torque, but you're going to pay in power. You're going to burn power to hold that torque on a stepper, okay? Now we have servo motors, all right? Servo motors can be AC or DC power. They have a controller device and an output sensor and a feedback system, because they're going to turn based on wavelengths that you send, wave patterns, to either 0, 90, 270, 180. Some of them can keep going, some of them can't. A lot of the less expensive ones only have so many degrees of movement that they can perform. Okay? They use what's called pulse width modulation. So the pulse width is going to change, and it's going to read that pulse width, and that's going to determine the angle that the motor is going to turn to. Okay? It's got 3 wires, power, ground, and the pulse width modulation signal. And that signal tells the motor, okay, here's your pulse width, go to that angle. And it just keeps sending that pulse width, and it's just going to hold that angle. So if you change the pulse width, then the motor will sense that and change the angle again. Okay, they're more reliable than steppers. They're constant monitoring of their position because they have the feedback, because it's going to turn based on the pulse width, and then it's got a sensor in it that's going to say, I'm there, I'm at 270, still at 270, still at 270. You put torque on it and it goes to 273, it's going to go, whoop, got to go the other way a little bit, I'm 273, okay, now I'm back at 270. Okay? So that feedback system is important. And these can be hard to tune if you need to, and that's really for larger systems, not the little ones we typically use in school. And the control loop, it does require feedback. So below, they say 1,000 RPM, it's not great torque. Stepper motors have better torque than these guys, okay? All right, now we're going to talk about brushless motors. The new drills that you can get at Home Depot or Lowe's, they have brushless drill motors now. They're very, very cool, okay? Brushes on motors wear out. They create friction, they create dust, they spark. So if you're working in an aircraft repair shop and there's an aircraft in there and there's fuel tanks around, you can't use a brushed motor for any power tool. They're in there with hand crank drill bit drivers to take screws out because you don't want sparks anywhere near a fuel tank, okay? And brushed motors create sparks. If you've ever used an old drill that's plugged into the wall, you'll see sparks when it starts up half the time if it's old and those brushes get worn. So it's alternating or inverting the power to drive each phase of a closed loop controller. So in a brushless motor, you're electronically flipping the power signal like a brush system would, okay? But you're doing it electronically to keep the rotation going, all right? So it removes the need for a commutator, which is the whole brush system that flips the power on a regular motor or an old-fashioned motor and a brush motor, okay? So advantages of a brushless motor: it's more efficient, there's less wear, okay, because it's being controlled by electronics, and it's got a very high torque to weight ratio. Light drill, lots of power, okay? It's got good torque, which dies off in a brush system as it gets older. And the only power limit is heat, okay? So if it gets hot, you're gonna lose power, but they don't typically get hot. I mean, I guess you could burn one of these out or overrun certain types of brushless motors, but if you're good to them, they are very, very, very nice and very efficient. Okay? That's it for motors, all right? You're going to see motors that we're going to use on robots and actuators, so that's really all I need to go into those for right now. In the next video, we're going to talk about real-time systems versus interrupt systems. There's a little bit of overlap and there's a little bit of difference, and I just want to make a point of going over it so that you're familiar with it, because real-time systems you are going to see on embedded systems. So it's something you need to be familiar with. See you on the other side.